Hi, welcome back, everyone. Third tutorial. So in the first tutorial, we did, the introduction to NFL Fast R, how to load in play-by-play data, how to, kind of manipulate that play-by-play data, get a basic like EPA per rush and stuff like that. Second tutorial, we did some more advanced data viz and stuff like that, and just made some cool graphs. So hope you guys have been getting use out of those so far. Always feel free to reach out to me on Twitter or email me and let me know if I'm going too fast or I'm going too slow, or there's something else you want to see, and I can throw it in the next tutorial. So today is tutorial number 3. It's going to be basic modeling with the NFL Fast R football data. We're going to make a logistic regression, and then we're going to make a linear regression too. So, hey, what's up, Jonah?
Hey, what's up?
All right, yeah, I'm just getting started here.
All right,
Perfect.
I missed last time.
Okay, yeah, no problem. So yeah, it's recorded. So
Great.
cool. All right. Okay, so first thing we want to do, as always, is load our packages. So the tidyverse package, the Ranger package, which is what we'll be doing our modeling out of today.
What I missed.
NFL Fast R package, and then GG themes is for this theme 538. Oh, Jonah, I'll send the in the chat so you can have it. In case you need to follow along, that's the GitHub with all the code that I'll be doing today. And then the variable importance package too, which will tell us kind of like when we build our models, which variables are influencing it the most and which variables aren't.
All right.
Run that. And then this is a custom theme here that I kind of built, which is just basically theme 538 modified. So I'll drop that in the chat. But it's not, it's not necessary to have that for the tutorial. It's just kind of to make the data viz look nice.
All right.
So now we want to load in the play-by-play data. So we're going to load it in from 2016 to 2021. So we can have play-by-play data pop up over here. So we can use the load underscore play-by-play data function from the NFL Fast R package to get that loaded in. Zoom in a little bit there. And then the next thing we want to do is we want to create a logistic regression model to predict based on the kick distance if a field goal is going to be made or not, or what the percent chance a field goal should be made by an average kicker from that distance. So what we want to do is we want to create a new data set called field goals. We want to take our play-by-play, pipe it, and then we want to filter and just get field goal attempt. And so field goal attempt will either be 0 if the play is not a field goal attempt, or 1 if it is a field goal attempt. So we can take 1 there. And then we also want to create a 1 or 0 column based on whether or not the field goal was made. Because right now in play-by-play, if we check kind of what the field goal result is, we can see that it's either made, missed, or blocked, or just NA or something like that. But we're getting rid of these NAs by making sure the field goal attempt is only 1. So we just want to put a 1 if it's made. So we can mutate a new variable called made field goal, and we can use our if else statement. So how if else works is if we do like the test or kind of what we're looking for, if that's true, we put like what we want it to be true for, and then if it's false, we put what we want it to be false for. So if field goal result equals made, so this is our test, we want a 1 in the made field goal column. If not, we want a 0. So we can run that and get our field goal data, which is now 5,500 rows instead of the whole play-by-play data. The next thing we can do after that is create our model basically. So we can create a logistic regression model. I'll drop this in the chat. We can create a logistic regression model. So how we can do that is we can use the generalized linear model, GLM, and we can do made field goal, then the little squiggly thing, and then we want to do it based on kick distance. And then, right now, if we were to run this, it wouldn't know where made field goal and kick distance are coming from. So we can say data equals field goals. And then since it's a 1 or a 0, we can say this family, and we can say it's binomial. So, if you ever want to play around with the other types of that, you can just type in $GLM, and it'll open up different types of things to do. So we can look at like family. So this is the one we want. Binomial is like Poisson distribution, which is what people look at interceptions through and stuff like that.
All right.
So that's how we create our model. Then we can check kind of and see, how well is the model at predicting, and we can use the summary for that. And so, we can see the estimate that kick distance has. So, as the kick distance gets greater, it should be negative because there's less of a chance they're going to make the field goal, stuff like that. And we can see kick distance is a significant variable because it has these 3 stars. So which means, based on whatever you want to do a significance level to be, if it's 0.05 when you're doing statistics and stuff like that, as long as it's less than that, that means it's an important factor in the model. And so now we can kind of make a plot and see, see the distances, what it's predicting for each distance. So we can call it pred prob. And then what we want to do is we want to take our log field goal, and we want to get the fitted values. So if we got the coefficients, that's this stuff that we were looking at here. We want to get the fitted values for each type of kick distance. So now we have a new column called predicted probability. And then we can plot this, and we can make the x-axis kick distance. And we can make a geom line which shows what the predicted probabilities are on the y-axis for each one. We can make those black, size equals 2. We can also do geom point to show where kicks are made and missed usually. So we can do made field goal, and then we can kind of color it based on whether or not they were missed, right? So if made field goal is equal to 1, then we can make it green. If not, we can make it red. And then let's make the dots lighter, so we can put alpha at 0.3 on a 0 to 1 scale. And then anytime we do colors with like these types of names and stuff, we need to do scale color identity, so it knows those are the color names. And we can add in our theme and see what that looks like. Oh, sorry, I didn't run this. So now we can see kind of the if we make this plot bigger, we can see kind of the predicted probability for each kick distance. So if they're kicking, if it's a 20-yard field goal, they're kicking from the 3-yard line. It's almost like a 99% chance that they're going to make it. And then we can kind of follow this line all the way here. If it's a 40-yard field goal, about like a 85% chance they're going to make it. A 50% chance they make it from like 55 yards out, and it kind of goes down. So this is what the model thinks is going to happen for each type of kick distance, basically. And then if we wanted to make the model look or sorry, the graph look nicer, we can just add our labels. So x-axis is kick distance. Usually try to avoid underscores. Y-axis is chance to make field goal on a 0 to 1 scale. We could multiply it by 100 if we wanted to, but we can leave it as that for now. So,
All right, I got all that.
perfect. So the next thing we can do is, we can do basically what we did here for the plot, but we can actually add that back into the field goals data set, because here we didn't do an arrow, we just had a pipe just for the sake of the plot. But now we want to add in our arrow. So predicted probability. And then we want to get our fitted values. So this will take each kick distance and it'll give the percent chance that they'll make it. And then we can create another new column on top of that called field goal over expected. So, we're going to take whether or not they made the field goal, and then we're going to subtract the predicted probability from that. So yeah, again, if they're kicking a 55-yard field goal and they have a 50% probability to make it, and they do make it, it'll be field goal over expected will be 0.5. If they miss it, it'll be negative 0.5. So we can run that, and then we can kind of open up the data set and look at the end here just to make sure it's a column. So yeah, we can see right here. So made the field goal, 68% chance to make it. So 31 or about 32% field goal over expected. So next we can kind of see the stats, because we want to, these are the individual kicks right now. So we want to group it by kicker, basically to see, who the best kickers are in the NFL just based on kick distance. Obviously you can add in, the weather and like the fields and stuff like that, but we just want to make a simple model here. So we'll take our field goals data set and we'll put it into this new data frame called field goal over expected stats. We want to group by kicker player name. And then we want to summarize based on that. And we want to count how many kicks they've had. So we can do kicks equals n open parentheses, close parentheses. We want to see what their expected field goal percentage is. Maybe some of them are like system kickers and they're always getting put in good situations, and that's why their field goal percentage looks really high. So this will take the mean of their predicted probability. Then we want to see what their actual field goal probability is. So mean of made field goal. And then we want to see their field goal over expected. So this is something, since we're gonna kind of make this into a plot, we'll multiply it by 100. Oops, field goal over expected. So all four of these things can be run in the summarize. So if we run that, we can open up our new data set and we can kind of see who was the best kicker. Matthew Wright for the Jaguars, but he's only kicked it 8 times. So we would probably want to put a filter on this if we were going to plot it, just because we're dealing with small sample sizes. So we can just pick something random like 50, and then since we can sort it just so it's easier to see when we open it up again. So now Justin Tucker is on top, 9.4% field goal over expected. Graham Gano second, Bryant Butker goes down. We can look at the bottom, Ficken, Mayer. This is from 2016 to 2020. I was sad to see Rodrigo Blankenship down here, but that's okay. Okay, so now you got all that?
Yeah,
okay.
Understood.
That way I can. Okay, cool. So yeah, so now we can make this into a plot. So we can take our field goal over expected stats. We can use ggplot. This one we'll want to do, we can put expected field goal percentage on the x-axis and then actual field goal percentage on the y-axis. That way we can kind of see who's overperforming, underperforming. We want a point for each player on the graph. So we can make the size the amount of kicks that they had, just so it's easier to see. And then we can make a fill for their field goal over expected. Since we're not actually plotting that, we can fill it so at least there's a color scale to follow along there. Shape equals 21 as usual. And then the color around the dot can be black. So the fill will be based on what they got, and the color on the dot will be black. And then we can choose a scale to that we want to fill it. So a very popular one is scale fill brewer, and there's different types of palettes you can do. Another one is scale fill Veritas, and so you can pick different examples. So this one is if it's a continuous variable, which is what field goals over expected is. This is a discrete variable. So, if it's if you wanted to show it based on like what round someone was drafted in, that's something that's like discrete, but this one's continuous. And then we can, so we didn't load the ggRepel package, so we can do ggRepel and the 2 colons to get geom text label. This is one way to do it, or you could just load the package. It doesn't matter. I just wanted to show how to do that. And then we can label based on kicker player name. So this way, each dot that we plotted here will have a label. And then we can just make the text size 5. Then we want to add in a line that shows how well expected field goal percentage correlates with actual field goal percentage. So we can do that with geom smooth, but geom smooth would shift based on the graph, and we just want more of a linear line that kind of shows the relationship. So we can do method equals lm. We don't want the standard error bars, which it's good practice to have when you're actually doing statistical analysis. But if we were to put this graph in an article or tweet it or something, we can take away the standard error by doing s equals false. We can make the color gray, and then let's make it bigger than 1. So we can just make it 1.5, just so it's easier. Add our theme again, and then add our labels. So expected field goal percentage on the x-axis, actual field goal percentage on the y-axis, and then actual and expected field goal percentage from 2016 through 2021. And then in our subtitle, we want to make sure, we're mentioning that it's 50 kicks. So we can kind of see how this plot turns out here. Yeah, so this is a good start for the plot. It shows there's a slight relationship between expected field goal and actual field goal. We can see Justin Tucker at the top, which is good, and exceeding expectations. We can see, kickers like Blankenship and Nugent had really high expected field goal percentages, but underperformed and stuff like that. But, there's a couple issues to the plot. If someone were to look at this, they wouldn't really know what the colors mean. So we can adjust for that by, in our theme, we can say we want a legend, right? And so there's some space at the bottom, so we can do theme legend position equals bottom, and then see how that turns out again. Okay. There we go. And so now field goal over expected shows up, and then kicks also shows up, but we don't really need the kicks one because you can kind of tell it's based on the size. So one of the things you can do to get rid of that legend is do guides size equals false because it's the size that we want to get rid of. And then another problem with that was field goal over expected was just labeled like this. So that's a variable that we would know, but someone looking at the plot might not know. So we can we can change it to like an actual name without underscores and stuff like that. So field goal percentage over expected. So we can mutate that column. And then we can use these little dashes so that we can have spaces in our column. And then we would want to replace this fill with field goal over expected. And something else we can add to the plot is just some more breaks on both axes. So we can do x continuous, y continuous. Now we can have our final plot. Oops. Oh, why is that sending? Huh. Oh, maybe it's too big to send in the chat. Okay, yeah, I'll just send each one individually. Okay, good to go there.
There is one thing. It says that I have no package called ggplot.
Oh, did you do sorry. In the last one we installed the package. So just type install.packages ggRepel like that. That work?
Yep, that works.
Oh, okay, perfect.
Thank you.
Cool. Yeah, of course. Okay, so now that we have our logistic regression model, we can kind of do something similar, but for quarterbacks. And we just got experience with logistic regression, which is modeling like ones or zeros. When we have a continuous variable that can kind of span over a bunch of different numbers, we can start off with a linear model. So something for that is like we can measure like a quarterback's air yards based on kind of the situation and stuff like that, because average depth of target is a frequently used stat when talking about quarterbacks. But if you're in more third and longs, often your average depth of targets can be longer and stuff like that. So we can adjust for that by creating a linear model and seeing which variables kind of influence it. So we can create a new, just like we did with field goals, we can create a new column called pass plays, where we just want passes. So pass equals 1. And then we want to make sure all the stuff we're going to be measuring doesn't have any NAs. It's like there's some passes that have sacks or get batted down and don't have an actual intended air yards. So we can filter out that. We're also going to be looking at down to see how that influences air yards. Score differential, I think, should be a pretty big factor. Yards to go from getting the first down, and half, like the seconds remaining in the half, like if they're throwing a Hail Mary or something. So yeah, put exclamation point is that NA, and then whatever variable we're looking at. So run that. Okay. So now, we have this pass plays data set, 100,000 rows and 372 columns, but we're not going to use all of those columns when we're modeling. So just to make it easier to think about, we can create a new data set called pass play model data. Use the arrow from pass plays, select, we just want air yards, down, score differential, yards to go, half seconds remaining, And then, so yeah, when we do that, we can just run that, and we can get our pass play model data, which is right here, basically. And so one of the things is it's going to treat all down. It's going to, when it does its linear regression, it's going to look at the difference between first down, second down, then second down, third down, and stuff like that. But it's not; those are not linear related. Just because third and fourth down are a little bit weird, and first and second down are treated like that. So what we can do is we can make the down column, which is right now right now it's numeric. We can make it a factor so that it doesn't treat them all the same. So we can just call it down again. We can just overwrite it, and then we can do down. So then now if we run str, which will tell us like the makeup of each model. Now it says factor with 4 levels. So 1, 2, 3, and 4. So that's what we wanted. Even though we filtered out the NAs, always good to check. Pass play model data. So call sums, parentheses is.na, then pass play model data. And it gives 0 NAs for each column. Okay, so now that the data set is ready to be modeled, we can make our model. So we'll call it air yards LM. We used GLM last time, so this time we can use LM, which is just the linear model. We want to, the response variable is air yards, so we want to put that before the squiggly, and then we have all the different stuff that we want to kind of add together to model air yards. And then again, the same thing is it doesn't know what data set we're getting it from, so we can say pass play model data. That. So that is just the one line you need to build a linear model. We can look at our summary now. Open it up. So we can see our residuals. So the difference between what our prediction would be and what the actual would be for air yards. We can see, so what it does is when there's a factor, it makes the first factor the intercept. So, it's showing up in, okay, so here, when something shows up in scientific notation, what you can type is options, scipin equals 9999. And then if you rerun it, it's a lot easier to see. So now it's not in scientific notation, which is nice. But we can see like which factors are significant. So it made down the intercept, so like that's the estimate that it has for first down, second down, third down, fourth down. Score differential, yards to go, half seconds remaining, we can see are all significant. Score differential was not a significant variable, so if you were thinking about like improving the model or something, maybe using something other than score differential would be better. And then we can also see the R squared. So it's 0.00. So we're basically not predicting air yards that accurately, which is okay because it's only a couple variables, and it's a simple model. Next tutorial we'll get into some more advanced models. So now we can see we loaded in this VIP package at the very beginning. So this is where it comes in handy, is we can see kind of the feature importance. So this is really helpful for more advanced models, like tree-based models and stuff. But we can still run it on this just to see which variables are important. So again, similar to what we saw here, where yards to go is really important. Third down and fourth down influence air yards a lot, which makes sense. Second down a little bit less because play calling is a little bit different there. Half seconds remaining probably comes into play for at the end of the half, and then score differential doesn't really mean much. So that's interesting that quarterbacks don't really get more aggressive if they're losing or less aggressive if they're winning. So now we can, like we did with field goals over expected, we can get predictions to get what each quarterback's air yards over expected are. So air yard preds, oops, air yard predictions. So this one is, so we're gonna wanna do predict.lm. We can, we can put in our model, air yards LM. And then the variable assignment is its new data. So it's the data frame which we want to predict off of, right? So we have pass plays up here. And so you have to check, or yeah, so it's pass plays, so it's good. And we filtered out all the NAs. So we can take that, and that's what we would want to predict air yards off of. And then, if we were to run this predict, oh, sorry. I forgot to do this here. So, when we mutated down as factor here, we would actually want to do it in the pass plays data set, because that's what we're going to be predicting off of, because that has the players' names, stuff like that. So we can just rerun that. Okay, good to go there. So when we run this air yard preds, it doesn't give us a data frame, right? So what it gave is kind of all this vector that we can't open. It's not part of these data frames up here. So we can wrap it in a data frame variable like that to get. Now we can see it pops up in our environment here. And so it gives this really ugly kind of column name or whatever. So we can see what the name is, and then we can see it's this whole kind of thing. So we wanna rename that. So we can pipe and we can do rename, and we can call it like expected air yards, because this is our prediction. And we can just copy that from down there and name it. So now we have our expected air yards data frame. And so now we want to join that back into the pass plays data set. So we can use a column bind function. So cbind, pass plays, and air yard predictions. So we'll call it air yard projections, just to have something different. It binds the two columns together. So now if we open up air yard projections, there we go. And we go all the way to the end. I'll dump this in the chat while it's loading. So now we're at the end, we can check, and there's expected air yards right here. So this is another example of a prediction, just like expected pass is right here, and there's pass rate over expected. So we would want to get air yards over expected. So how we can do that is air yard projections. We can put it into the same data frame, and we would want to mutate and get air yards over expected, which would just be their actual air yards minus their expected air yards. And so now we can get some air yard over expected stats for this season. So yeah, we can filter the season to be 2021. We can group by passer, just like we did with kicker earlier. Summarize the amount of passes we want to check. Summarize what the average air yards over expected is. And then let's just filter for like 100 passes or something, just 100 passes, so that we don't have small sample sizes. So Lamar Jackson is the leader in the NFL in average air yards over expected. Baker Mayfield, Josh Allen, Matt Stafford are up there. And then we can look at the bottom. Jared Goff, Kirk Cousins, Matt Ryan are throwing under what, kind of the model expected them to. So all good there.
Yep, all good.
Awesome. But yeah, so those were how to build the logistic regression and the linear regression model. If you're watching on YouTube, the link to the GitHub code, or you could come to my GitHub and just go to the NFLR tutorials GitHub page will be there. So follow along, and I added some comments, so that'll have all the stuff you need to make those two models. And then for the next tutorial, we'll be doing kind of random forest, which is a tree-based model, and then and some other more complicated ones. But yeah, this is a good start for now, for sure. Cool.
All right, excellent.
Yeah,
Thank
no,
you. Of
yeah, thanks for coming.
course.
All right,
Have a good
bye.
rest of your day.
Yeah, you too, Joanna. Bye.
Stuff.